So move semantics. Need my chat window, otherwise I don't see what's happening. Okay. Okay, so in C++ 11 on, there was this shift from the old the old classification of L values and R values into a more complex hierarchy. So before C++ 11, we had the R value and the L value, where R stands for right and L for left. So a left value is something that can be on the left side of an assignment, and an R value is something that can only be on the right hand of an assignment. If I say x equal 10, and x is a variable that is an L value, and 10 is an R value, because you cannot modify 10. You cannot say 10 equals 15, right? It's just 10. What the discussion about the ability to implement RAI, which is resource acquisition, is initialization, that we will see more in detail later, is and the fact that you want to pass heavy arguments to functions without copying, right? The whole thing. I want to pass a vector, and I want to give the vector to this function. I don't want to make a copy of the entire thing. It turns out that the simple distinction between R value and L value were not sufficient. And so there are this complex hierarchy here, where the L value is still here and the R value is here, but the R value is turned into a pure R value, like 10, right? That's a pure R value. And the X value, which is the expiring values, they are like the one that we saw in an example earlier with the decal type, where you were constructing an object when calling a function that is an expiring value. It doesn't exist after the function. So after the function is being called, after the function is returned, so then that is expiring value. So let's talk a little bit about references. As we said, the reference is not an object. It's one of the few things in C++ that are not objects. And the tref, where t is whatever type, is called an L value reference. And this is used to alias a pre-existing object. So if I have an int x equal 10, and then I have int ref y equal x, y is basically an alias. Is another name for x. They point to the same memory location. C++ 11 introduces the tref notation, so double reference. And this is the R value reference call. What does an R value reference do? Well, technically, the only thing it does, it extends the lifetime of a temporary object. So suppose that I have in C++, even right now, you could do const t reference x equal 10. Suppose that t is integer, is int, right? Then you can assign that is a constant integer. It is a reference for some reason, but it is a constant. You cannot change it, and it's a 10. But if I do x++, this gives me an error because it's a const. I cannot change the value. Instead, if you use tref x equal 10, it is still an R value in some sense, but you can modify it. Now, if you take it like this, it's just confusing. You don't get it. Why do you need that? This is just a technicism. It's just a technical part that allows you to use this notation in overload resolution. So I have a function, I'm calling a function, I have different versions, I need to select which one to call, and this one is an additional possibility. So suppose that I have a function f that takes an integer reference in input, and a function f that takes an int ref, so an Rvalue reference of x. And so in my main, if I call f of x, where x is a variable, I go to the first implementation, to the one that accepts the reference. If I call f10, I go to the second version, so the one that accepts reference. You can also instrument the member functions with the ref and ref, and this basically qualifies this pointer of these functions. So you basically, if I construct my object A with the curly braces, I default construct my object and I do call me, I go to the one that has the ref. If I say A, which is not, my object, which is alive on the stack, it is allocated and exists, call me, then I go with the ref version of it. So what can you do with this? So the idea is that now I can really specialize my functions for something that is created on the fly, for instance, or something that I don't want to take care of anymore. I want to give it away. I created an object, might be a heavy object, but I don't care to have it anymore. You just can give it very efficiently. Let's consider a movable container, right? The container is a piece of memory. It contains something, and then you have interfaces to access the data and to maintain some information over the data. Like in this case, the most typical container you can have, you have a pointer to some region in memory, and the size that tells how many elements there are. Very simple, basic container. I call it movable, and I'm saying that when I construct with a size, I create a new pointer, basically allocate a new piece of memory with s integers, and my size become the size that I just passed in. All right. So now this is my container. I instantiate it, and I do, and I keep my pointers around and keep my storage, and how big it is. Now I can implement a copy constructor for my object. So the copy constructor takes the name of the class here, the name of the class const ref, and then the name of the variable. And here I need to do something interesting, something peculiar. I say if my pointer is not a null pointer, so if I'm actually pointing to some actual memory, so this movable array was already allocated, then I will delete the memory. So I free the memory, and then I can take the size of the other guy becomes the size of me. I allocate a new piece of memory with the size S, that now is the new size, and I copy the other one, the other container, into my newly allocated memory. All right, so this is how I do a copy. But what if now I want just to move it? So I want to give it to this object. I don't want to make a copy. I don't care about copying. I need to just take it. Take the guts of this object, move it on the other side. Then I need a move constructor. And the move constructor behaves like, is specified like this. Is the name of the class, the name of the class ref, and then the name of the other class that they're passing in. Now, in this case, what happens is the following. The current pointer becomes the other pointer. Well, probably needs still to delete, I guess, if it is already allocated, but yeah, it's a movable, no, it's a move constructor. So you take the move, you take the pointer, of the other guy, you assign it to yourself. The other pointer you set to null pointer. So the other guy doesn't own the data anymore. And then the other size become my size, and the other size then becomes 0. I stolen the content of the other object, keeping the other object consistent, right? I keep the other object valid, it just doesn't contain data anymore. And now this new object owns it. So, and this is how you define the move constructor. The move semantics still in the guts while leaving the other object consistent. And now you can see the performance issues here, right? But now before you had to copy, and now you just move a couple of pointers. You just have few instructions instead of copying a whole bunch of memory. So when I construct the movable object like this, I construct the movable object with the size 200. This is basically an unnamed object, right? It's a temporary object, it's unnamed. It is an Rvalue reference. It creates an Rvalue reference. So it binds to the move constructor, basically, right? Movable Z with the movable 200. If I already have Z and I want to move it and steal the guts of this guy, then I say U std move Z, and std move basically convert the type into an Rvalue reference. It doesn't do it. Std move doesn't do anything. It just changes the type. It's a function that returns an Rvalue reference to Z, basically informing from now on Z will be moved, right? So it's probably std move should be called something like I'm going to move it. And then, well, the question is, well, do I need a destructor here? We go with the rule of a rule of 5 in some sense, right? Now I have this dangling. We have a pointer here. If when I destroy this class, I will destroy the data members, but do not free the memory that I allocated. So I need a destructor in order to clean after myself. I did my work. Now I'm destroying. I need the destructor to free. So let's see another version of the movable. Now you can see the code is actually much shorter, right? The fonts are bigger. So we have the same behavior as before. Instead of having a size and a pointer and a size, and just keep an std vector as a data member, I call it V. My constructor has exactly the same interface as before. It takes the size, then I instantiate my vector with that size, and that's it. Now, vector is a move-aware object, which means that if I'm doing a move, if I do a copy constructor, I can simply say, well, I take this other guy, so movable const ref is a copy constructor, and then I call the copy constructor of the vector. And then if I do a move constructor, I need to do, the signature is exactly the same as before. So name of the class ref, and then the name of the other variable that I want to use. And then I say V, my data member, is constructed with the move from the other into this new vector. And I need to do std move at this point. And the reason is that other has a name now. As we saw in the first slide when I introduced the ref notation, you could modify now other. Now other, yeah, it's an Rvalue reference. It has extended lifetime. I can do work with this other. I can add element, I can remove, I can work with it. But in principle, the only thing I'm allowed to do is basically take it and move it somewhere else. So now I'm basically saying std move other v. So I need, since it has a name, I need to move the other vector into this new one. And that's all I need to do. The advantage of this is that I don't need the destructor anymore. This is all you need to do in order to have a movable container. Yeah.
And I would say that I would say even more. You don't need to define your constructors at all, because it will be already movable by default.
Yes, exactly. So this code is actually, you don't actually need it, right? Because the default constructors are already kind of working for you. But I want to show you a little bit. I want to, let's see what happens, right? So sometimes you want to understand what happens. So you put like prints into your constructors to see what happens. So now we put the constructor print into the basic constructor, and we put another one into the move constructor, and we delete the copy constructor. So we say, I don't want to move, I want to copy. Every operation I want to do has to be move only. I don't want to copy. I'm so concerned with performance that I want to avoid the possibility of copying these guys. What happens then, you say movable 200. Here we can see the size. This show is basically a macro that I've defined in my examples. And then you move z into u, and you want to see how things work. And now what happens if you run this, you say that you see construct, you basically do the destruction, you construct. But before seeing this print, which is this guy, there's no move. So it's not moved. What happens is that the move constructor is not called. So you are constructing here, and you're not giving it, and you're not actually them doing the move. This is an example already also mentioned earlier, is that if the compiler sees that this can go straight, this is an expired value, and so who cares where you construct it? So you do the construction directly into Z. So this side effect that you're putting here to see what happens doesn't show up because it actually doesn't happen. And so you should always be careful to put the side effects into the constructors of your classes. I think I removed the, no. Yeah, so when I then move U, when I move Z to U, then after that, Z size is 0 because it has been stolen, right? So the Z is still in a consistent state, but it's empty, and U is now has 200 elements. Without any copy, though. And try to remember what I was trying to do here. When is the move triggered? Yeah, so you construct and you see the sizes here. When you put so you want to see the copy and the move. Well, you see, now I also allow the copy. And now when I do the copy, I can see the copy happening here in this instruction, and I can see the move happening when I do the move, but I don't see the move over here. So yeah, this is basically redundant actually with the previous thing. So what if I don't want this object to be movable? Well, actually, what happens here is that, so we have seen here that this move constructor is never called, right? This is never called. Movable to 100 is constructed and then moved to Z, but actually never moved to Z. So now I want to delete my move constructor. I want to also delete my copy constructor. Just I cannot do anything. Will this work? This code work? Well, clearly it doesn't. And you have a compilation error because it is trying to call the move constructor. So when you write this, it search for the move constructor. It doesn't call it, but it looks for it. It's saying, is this object allowed to move? Can I do this operation? Is the semantics of this object involving the moving or not? So if we don't define the move constructor, this will not work. If you define the move constructor, in this particular case, is not called. You don't call the move constructor. And this is why it's called the move semantics. It's not the move syntax. Let's say an almost real world example. So in this case, we want to take strings from input, and we have a vector of strings, and we want to push the strings into the vector. So now instead of just do vector pushback of the input of this string, we just do the pushback of the move of the input. So pushback in the vector has two different overloads. One that takes the constant tref, so it makes a copy, and the other one that moves it. If I move it, I take the string, I steal the guts of that string, and I basically now the vector owns it. It owns that string. So even when then input goes out of scope and disappears, the vector still contains the proper strings. And you're done that without copying any, you're not making extra copy here. Subtleties, I think this is what we had before. No, okay, this is something else. When you design your classes, be careful that you don't replicate the information, or you don't make any redundancies, and you just keep your information clean and in one place. So suppose I have the struct movable, and before, if you remember, I had to do this, right? I was z.v.size. So I was accessing the data member v and then asking for the size of the vector v, right? Now I want to say, well, you know what? Let me just put the data member s with the size, right? And now when I do my movable, I instantiate my vector, and I set my size to whatever size it is. And since the vector is movable, since the vector is move aware, and everything seems to be move aware, so I don't need to actually that I don't need to implement the move constructor and the copy constructor, as Anton was saying, right? They were just given to you automatically. But the problem is that if I then take my movable z200, I moved it into u, then the z.v.size is 0, but z.s, so the initial size, this variable here, is still 200. So the object is an inconsistent state. And why? Well, simply because the trivially movable objects are actually copied. So an integer is copied, is not moved. And if you think about it, it is really not clear how you would move an integer, because an integer, what does it mean? Does it become 0? Does it become 2 to the minus 32. What is it? What numbers should represent a not integer? So actually, when you copy trivially movable objects, which are basically the also PODs, for instance, they are trivially movable, then you are making copies. So it's in those cases you need to be careful and embed your semantics, what that size means. Yeah.
Well, I have a short remark about that. So in principle, after you have moved from the object remains in so-called zombie state. And
you shouldn't be using the same object. Yeah, that's
yes.
true.
And the standard only allows to use destructor with this object and nothing else.
Yeah, that's right.
And in principle, this the fact that you call in the show after the object have been moved it can lead with can be undefined behavior, and actually regarding the moving of the integers, it's not completely true, because compiler can left those integers in undefined state, so it can be anything. And this is a real case. So if this object is not is temporary, if compiler can detect that this object have been moved, and it can decide to construct, it can decide to optimize this object out completely, and this show can in principle it can show not 200 but some garbage even. Thank you.
Yep, thank you, Anton. Yeah, I wanted to show what the behavior, how things are done. But thank you, Anton, you for these remarks. What happens when you have templates and Rvalue references? Well, in this case, we talk about universal reference. So if I have a function foo that takes a tref x, where t is the template argument, and I'm asking, I want to check, is the type of decal type x what is it? What is the type of this guy? So in case of if I pass foo of I, what happens? Is it an integer? Is it an integer ref? Is it an int ref? If I say that the type t is int ref, so I'm just forcing it, I want it to be int ref, is it going to be, it will be int ref and then followed by ref. Is it what that happens? If I say 42, what will be the type of this x here? So the rule is the following: if t is a ref, or is a if this is a ref, then appending the ref like here, right, which you are substituting, gives you a reference. If you have two refs in a row, so if what I'm passing is the t ref, and then appending this ref gives you the ref. In all the other cases, you have t ref. So it means that whatever you're passing here in this various cases, apart from the foo 42, in which the decal type of x will be int ref, the other one will be all int ref. And this is just a rule. So if I have an integer I equal 10 and an integer ref a equal 10, okay, this is a different story. So now I have, so A, it will be int ref, right? And then I would be int. And now I can add the ref also to the auto keyword, right? And in the auto keyword, you use the same mechanism as template deduction. So you have basically the same syntax here, right? Auto ref C equal A and auto ref B equal I. But then when I ask the type of C and the type of B, I will have different results. In one case, int reference, in the other, int ref reference, because here A will be int ref, so int ref, still ref. Here is int ref, and so int ref is ref. So the only case in which you can get the ref is when you concatenate to refs. So suppose now that I have my class X, which has a pushback with a tref and a pushback with a const ref, like the vector, right? So I say X pushback 3 and a pushback I and a pushback J. What happens here is that the first one will go to the ref, of course. This one will go to the const ref, and this one also goes to the const ref because J is an int reference, is a const int ref, and then you go to the const ref. But now, suppose that I'm templating instead of templating the class, the type name T, I'm templating the member functions with the template T name. What happens in this case is that the first one goes to the ref, the second one goes also to the ref, but it is a reference again, right? Because this one goes, it becomes int ref and then gets into ref here. So I go to this one, which is not, because this is not const, right? I is not const, it can be modified. So it goes there, it makes sense. And this one goes to the const ref because it is a const reference to something. So you have slightly different behaviors depending on if you are templating the class or are templating the member functions. One important thing though to understand is the forward, is a perfect forwarding. So when you want to pass to the next function, maintaining the value category of your incoming arguments. Suppose I have a bar int ref x that increments x, because now x is, you can do the change, and if it is not value reference, it does nothing. So in this case, I want to call foo, and foo will call bar for me. So foo would do something and then call bar, for instance. And now, when I call foo of I go here, I become an int ref. And so I need to call the ref one. So I forward x to the next function. So whatever type this will came in, it will be forwarded to the right one. So if I say foo int ref, then I go again to the top one. But if I say, oops, foo 42, it will go to the int ref. So if the decal type of x is tref, so if t is actually, if the decal type of whatever comes in here is not really t, but it's whatever t is here after the template type deduction. If that is an Rvalue reference, then x is an Rvalue reference and you go to the Rvalue reference. Otherwise, you go to the reference version. And this is important because when you want to abstract you want to abstract the layers underneath you, and you want to maintain the semantics in the right way, you want to use this forwarding so that you maintain the value semantics that of the function that you call. And you cannot do std move. So if we move here, this will always be interref, right? Because std move would always add the ref at the end, so we always go to the second option. But sometimes you want to go to the second, and sometimes you want to go to the first. Would take probably some time to get used to it, but that's how it is done with the forwarding.